In the previous slide, we saw an example that showed us, at least in this example, that fxy and fyx were both 2x cosine y, that they were equal. And it turns out, this is called Clairaut's theorem, that if fxy and fyx are defined and continuous near a point, then they're equal. So it turns out that fxy at P and fyx at P are both the same. So why is this a useful thing to know? It's useful if, for example, I want to compute f x, 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 let's say 6 x's and then a y, of f of xy is equal to maybe x to the 100 power. Right, on one hand, I could take a derivative, a partial with respect to, on one hand, this is the partial with respect to x of f, then a partial with respect to x again, x, 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 then y. Or by Clairaut's theorem, so we could sit down and we would be working this out all day, right? I mean, well, maybe not this function, but it could take a long time, right? Or by the theorem, we could take the partial with respect to y first, because it turns out that fxxxxxxy is equal to f, y, and 6 x's. So I could take a partial with respect to y first, and then partials with respect to x, so 5 x's or 6 x's. And the reason this is useful here is because what is the partial with respect to y of f? If f is just x to the 100, that's 0. So 0 and then 6 derivatives with respect to x, this is just 0. And so maybe, I mean, this is a convoluted kind of contrived example, but it may be that you're looking at a function that is very difficult to take a derivative of with respect to x first, but if you take a derivative of it with respect to y first, then the function becomes much simpler. And so this is something that we definitely can use.